Hi, I'm Bob. Let's solve the problems at the end of Chapter 5, Multiple Regression Analysis, OLS Asymptotics, from the textbook Introductory Econometrics, a Modern Approach, the 7th edition. For the first problem, we need to show the consistency of the intercept estimator beta 0 hat. We obtain the OLS estimators beta 1 hat and beta 0 hat from the simple regression model. The beta 0 hat equals y bar minus beta 1 hat times x1 bar. This is a property of the OLS estimators. The OLS regression line goes through the point of the sample means. We plug in this expression and write the probability limit into two terms using the property of the probability limits. Let's look at the first term. The probability limit of y bar equals the population average, mu y, or the expected value of the random variable y, by the law of large numbers. Similarly, the probability limit of the sample mean of x1 equals the population average mu x1, or the expected value of x1. We also have the consistency of beta 1 hat. That is, the probability limit of beta 1 hat equals the true parameter beta 1. Put all these into the expression, and we have the probability limit of the intercept estimator equals the expectation of y minus beta 1 times the expectation of x1, which is the beta 0, since we assume the expectation of the error term is 0 under the Gauss-Markov assumptions. Let's find the answer to the second problem. Suppose the true model is a multiple regression and the estimate model is a simple regression. The variable risk tolerance is omitted from the estimated model. Using the inconsistency formula in the textbook, the probability limit of beta 1 tilde equals beta 1 plus beta 2 times delta 1, where delta 1 equals the covariance between the variables, the number of mutual funds and the measure of risk tolerance divided by the variance of mutual funds. If funds and risk are positively correlated, then delta 1 will be positive. Therefore, the sign of the inconsistency depends on the sign of beta 2. Usually, a higher tolerance for risk leads to more investment in the stock market, so beta 2 is positive. Then the inconsistency, beta 2 times delta 1, will be positive. So we overestimate the effect of mutual funds on investment in the stock market. Let's do problem number 3. The answer is no. The average number of cigarettes smoked per day by single adults does not have a normal distribution because 497 out of 807 individuals in the sample do not smoke. When we summarize the variable in data, we find that more than 50% of the observations have 0 cigarettes. The skewness and kurtosis indicate that it is not a normal distribution. We know that a normal distribution has 0 skewness and its kurtosis equals 3. We can also graph histogram plots for the variable using the histogram command. It is really right-skewed. Let's find the solution to problem number 4. For the simple regression model, we define a variable z as any function of x. The textbook shows that the slope estimator is a consistent estimator for beta 1. Now, we need to show the intercept estimator is also consistent for beta 0. As in problem number 1, we use the property of the probability limits and write the probability limit of beta 0 tilde into two terms. By the law of large numbers, the population averages, mu x and mu y, are the probability limits of the sample means of x and y. Plug them into the expression and we reach the final answer under the Gauss-Markov assumptions. Let's do the final problem. Consider the equation y equals beta 0 plus beta 1 times x plus beta 2 times x squared plus mu, where the explanatory variable x has a normal distribution in the population. The first question asks us to show that we can write y as a function of alpha 0 plus beta 1 times x plus nu. We can compare the two equations and find that nu equals beta 2 times x squared plus mu, and that alpha 0 equals beta 0. In the second part, the expectation of nu conditional on x equals beta 2 times the expectation of x squared plus the expectation of mu conditional on x. For a standard normal distribution, the expectation of x squared is 1, and the expectation of mu is 0 by assumption. So the expectation of nu conditional on x equals a constant, beta 2. In the third part, we plug in nu and then write the covariance as two terms. We know that the second term is 0 because of the zero conditional mean assumption. The first term is also 0 because we can use the covariance formula to write out. The covariance formula is as follows. Finally, the covariance between x and nu is 0. In the fourth part, we use the probability limit formula. From the last part, we have the covariance between x and nu equals 0. Therefore, the probability limit of beta 1 hat equals the true parameter beta 1. In other words, the OLS estimator beta 1 hat is consistent. The last question. For a nonlinear relationship between x and y, the linear estimation only fits the data around the sample mean well, but it has poor prediction at the tails of the distribution. So, being able to consistently estimate beta 1 and beta 2 is more valuable than just estimating beta 1. Thank you for watching this video and subscribing to my YouTube channel. See you next time.